Alright, in order to create the pallets, we're going to use a box. These center points would adjust where the center point is relative to the box, so we're actually not going to adjust those. For the length, we're going to do 110 by 110 millimeters, and for the height, we're going to do 20 millimeters. This will create the basic box. Now, in order to actually create the divots, like what you would see in the lab, we're going to use a cylinder. And for this one, we are going to offset based on the base. So, for this one, we're going to do 20, 20, and 10 here. We're going to do a radius of 10, and we're going to actually give it a height of 15. This way we can see it poke over it. So when we hit create, we're going to have that there. So we're just going to continue making cylinders so that they peek out. So this one's going to have a x offset of 20 and a y offset of 55, along with a z offset of 10. This will create the next one. Moving forward, we'll do 20, 90, and 10. This is so that we have a x and y offset of 35. So as we're going through, we're going to adjust the x and y offset, or if we had different pallet shapes, we can change the x and y offsets. But for this example, we're going to go through and continue making all the cylinders. Once all of the cylinders are completed, we're going to close that menu. We are then going to select the subtract function. So the primary one is the body that we want, that's the resultant, and the width function is what we're actually subtracting. I'm going to unclick Keep Original, and now when we hit Create, we'll have a hole in that spot. So it's actually going to create a new part every time we click it. So in order to do that, you just click here, then click here, unclick Keep Original, hit Create, it will make another part. Now it will actually replace the original part as you do this. So you won't have a ton of parts, but you will have the resultant part made every time you do this. I'm going to keep on going through, and I will complete the full palette here. And once all of the units are subtracted, we can hit close and we'll have a singular part. Now, this part consists of a geometric body, but in order to make this a little bit more usable, if we hit F2, we can rename the part. So I'm going to rename it palette_A. And that's how you make a palette. Now, in order to make two of these pallets, we're going to click empty part. It'll have nothing in it. We can actually copy this and paste it into the next part. Now, in order to move these parts into position, we can go here, position, offset position, and we can actually move it however we want in our coordinate system. And so, for a brief example, I'm going to move this 100 here and 100 here. And if we apply it, it moves it as we want it. And we can continue moving it along this offset as we so wish. We can also rotate it in our offset. So for example, one of our pallets has a 30-degree offset. So in order to accomplish that, we'll hit 30 degrees on this and apply it. After creating our pallets, we're going to go through the process of making a gripper. So we want to start our workstation with a robot in there, as well as a virtual controller setup, and this will become important later. So step one is we want to go to modeling, but we also want to make sure that our robot is invisible. This will help set the dimensions for our various components that we're going to use. So starting with it, we're going to make a very simple gripper. So we're going to set this length as 60 millimeters, this length as 30 millimeters, and this length as 10 millimeters. And then we're actually going to offset it since the center of this block is the center of the origin point, which means that our offset here will be -15 and our offset here will be -30. We are then going to hit create on this. Now, in order to model that gripper with a decent amount of accuracy, we're actually going to make the length of it, we're going to make a cutout in it. So we're going to make the length of 60, a width of 30, rather a width of 25. We're going to give it a height of 10. we're going to give it a center point offset of negative 12.5, offset here of negative 30, and then we're going to bring it up in the vertical direction by 10, or rather 5. By doing this, we'll be able to use the subtract function like we did earlier in order to create a sliding feature. So going through that, we're going to use subtract. We're going to select the bottom object with 5, a length of 10, and a height of 40. And then we're going to offset this one so that it fits nicely within our framework here, which means that the center point is going to be displaced by negative 12.5, and the vertical position will be an offset of 5, and here we will offset it, let's see, 10 minus, we will offset 20. Now, by doing this, we can set the origin of this point exactly where we want it to be. So we're going to hit create. Going forward, we're going to make another one of these objects pretty much the same exact way. So, same length, same width of 25, same height of 40. We're going to offset it again, this time negative 30. Set this to negative 12.5 and set this to 5. And now if we look at this, they have, I believe this was a width of 10. No, that was definitely 25. So now we have these things set up. However, just to make it easier to see, because you can't tell whether, it's a 180 degree rotating, I'm going to set the color of this one to blue and set the color of this one to red. So now, when we're moving this around, we'll be able to very easily see where it is. Alright, so moving forward, we're going to hit the Create Mechanism button. We're going to change it to Tool, and then we're going to hit Links. So we have to define the 3 links that we're using. So we're going to select this component as our base link, tap it into there, hit Apply. The L2 will be part 4, hit this button, hit Apply, and the L3 will be using part 5, and we'll hit Apply. Then we have all of our links defined. Now we go to the joints. So we're going to select prismatic so that way it moves linearly. L1 is the base link, L2 is going to be the component that actually moves. So as you can see, once we define our axis direction, we're able to move along that axis. So we're going to set the maximum limit of that to 0 and the minimum limit to negative 20. This way we can move it to the center and have it actually close. So we're going to hit Apply. It's going to automatically move to the next one. This one we're also going to set the axis direction to 20 and moving. We have to change it off of prismatic, or change it to prismatic. This way it does that. So we're going to set the maximum direction as 20, or rather 30, and the minimum as 0. This way, when we move it, we can move it in towards the center. And rather than being 30, I will set it to 20. This way it closes in on that center. When we hit Apply, it will save it. So now we have everything saved. So now this tool data is pertaining to what actually the weight of this is. Now, we won't really be using this in our simulation, but it is a good thing to know. So we have to define where the center of this tool will be. For ease of reference, I'm just going to give it a 1 kilogram mass, and I'm going to offset it to roughly the center of this base link. So 5 millimeters up, I'll hit OK, and that will satisfy all the things for the mechanism. So now when I hit compile mechanism, it actually sets it. So moving forward off of that, we have to define what the actual poses are for this. So we actually want to take this menu out and do a float on it, so that way we can actually get to the lower areas of it. So right down here, we want to add this. We're going to have a home pose, or rather the open position. We're going to hit apply because that's where we are right now. And then we're going to have a closed position. Now, this software does allow for physics simulation. However, we're going to have to move these. And I've set this wrong. Okay, so this is a common issue that you'll find where one of these will move, but then both of these will move. This is due to the joint definition. So we actually have to go back to joints, and as you can see here, L3 is defined as the parent link. So if we actually look at this, we have to change this back to the base link. This will now allow that to move as intended. So now, if we change this to closed, and we move this joint, hang on, we have to recompile it. So recompiling it actually helps that. So now, when we go to this, we'll give a open position declaration. Now if we move this one, that moves just nicely, and we will do a closed. So now if we move this one and this one, we can get them to actually be where we want. So we're going to move it to -11 because we want a distance of 18 in between them. So if we move them both to 11, we'll have a rough display of where the block should be. So if we hit apply, once we have our gripper attached to our robot, we want to actually make it so that changing a signal will actually change the gripper position, so we'll be able to move the pose. So the way that we do that is, first of all, we have to create the actual signal. So we go to configuration, IO system. We're going to go down to signal, right click, new signal. We'll have to give it a name, so we'll just call it Digi. Type of signal has to be a digital output. This is just how the clause. Access level has to be set to high, all. We'll hit OK. Now, after this, we're going to have to restart the rapid controller. So what we'll do is we'll go to rapid, restart rapid P start, and give it a second to restart there. And once it's connected, we can now go to simulation. If we click this little drop down here, that will open up Event Manager. As you can see here, we already set it up to run through, but if we wanted to go through the process, we'd go, create new event, add, activation on. It's an IO signal changing, so yes. So hit next. We're going to scroll through, find our signal here, which is Digi, and we have to set, one for the true condition and one for the false condition. So we'll hit next. So we'll actually change it to move mechanism to pose. Hit next. We're going to select the gripper, and we have the two poses that we can do. So the home pose is the open pose, and the closed gripper is the closed pose. So we can set it to this. We'll hit finish. So now, when we hit 1 on it, it will move it to the open position. And in order to make sure that it can go to the closed position, we're going to do the same process, but instead of using true, we're going to use false. Same setup. Select my gripper, select the pose as the closed gripper, hit finish, and there you go. So now we can test this out by going to our digital controller. Acknowledging this, going to our inputs and outputs window, hitting view, hitting digital outputs, and now we can see that we have this one as well as Digi. Digi is the one that we just configured. So if we move the controller and we hit 1, we can see that it goes to the open position. If we hit 0, we can see that it goes to the closed position. So doing so, we can actually change it, and using the set and reset commands in our code will actually close and open the claw. We also use this for setting the attaching logic. So after we model the gripper as well as the post, we're going to go to simulation. We're going to go to station logic, and we're actually going to write a very, very basic logic so that we can attach the gripper to the post. Now, this program allows for some very basic physics simulation. However, we're not really interested in the physics of how the gripper grabs the post. In this essence, we just want to make a very simple, attach to. So, using the signal which actually changes what the gripper is, we're going to go to Actions, Attacher. We're going to set the parent as the actual gripper, which is the My mechanism, and the child object is part 6, which is our post. We're going to hit Apply, and it will save our changes. From here, we also have to make the logic for if it wants to detach. So, using the logic gate function, we're going to change it to a not, and we're going to drive this signal to it. From here, we can attach a detacher with the child object of the actual post object. We'll hit Apply, drag this over here, and connect these outputs. So now, when our program is actually running and this signal is changing, we are attaching and detaching as needed. After getting our gripper in order to attach to the post using the simulation logic, we now have to train it the actual points that we want it to go to, as well as the work objects. So, in order to train it with the work objects, or rather, in order to get there first, we have to define the tool object. So, we do this by going to Program Data, Tool Data, New. We're going to name it Tool2, hit OK, then edit it, change declaration, then edit it, change value, go down here. We're actually going to move the Z offset due to the length of the blocks, so we're going to set it to 40 millimeters. And down here, for the mass, we're going to set it to 1 kilogram. This is just an approximate value. It doesn't really have any bearing on our simulation. And then as for the position of it, we're going to set it roughly equal to where the base is, so we're going to set it to 10 millimeters. Hit OK, and this tool is now built. Tool 1 is the tool that we actually use for all of our code, but showing the process is important. So, moving forward onto what the actual work objects are defined, or rather how they're defined. So, what we'll do is we'll go back to the program data, we'll go to view data types, we'll go to work objects, and you'll see that we have work objects 0 and which is the default one, work object A and work object B. These are objects were defined by going to edit, define, and we used a 3-point define. Now, in order to do a 3-point define, you're going to need to know the points that you actually want to go out to. So, knowing that this palette has an origin point, which can be found by going here, and then using the set position command, we can see that we have a X, a Y, and a Z of 295, -170, and 0. So, on our teach pendant, we're going to go to the jog command. We're going to make sure that we're in the universal work object. We're going to set our tool, which, yes, we did set tool 2, but tool 1 is the same thing. Make sure that we're in linear, and we're going to watch these positions very carefully. So, we want to get our position to 295, so we're going to move like so. Change to small increments so that we have a higher degree of accuracy. and we're just going to move this all the way until it gets to 295. We're also going to do the same thing with the Y condition. And while we could move our work object all the way so that it's a 0 on the base axis, we're going to adjust it so that it's 60 millimeters above where the 0 point is in the work or default works frame. So 295, we're going to adjust our Y using the larger increments. So we're going. It's always a little bit of a touch and go situation, but we see X of 295, Y of negative. This Z we're going to bring down. And there we go. So if we move the teach pendant, we can see that we are directly above this origin point. So now we'll go back to our program data. We're actually going to, so we have work objects defined already, but edit, define, 3-point definition. So right now what we have is our origin point. So we're going to hit modify position to actually record it. Now what we have to do is we have to define a offset X position as well as a Y position. So knowing that we know the X and Y, we're just going to increment slightly. Now we have to move in the positive Y and the positive X to determine that our Z condition is in the right way. So using this joystick directions, we're actually going to just move a little bit. Now personally, I just like to go 10 because it's very simple and easy to do, but it could really be however you want it. So we're just aiming to, 305. We're going to touch it up a little bit in the Y, and the Z shouldn't have to be adjusted at all. Just a touch. Yep, so this will be our new X, and then as for the Y condition, we're actually going to reset it back in the X. So move this back to 295. I find that it's usually better to just ride it out in the slower condition than using the no limit, because oftentimes you'll get a lot of overshoot. So just very slowly but steadily we're going to go to this location. Yep. Alright, and now we're going to adjust in the Y. So we're aiming for a target position of a negative 160. So, we overshot, but we're going to very slowly crawl back. Yep. So we have achieved the position we desire, roughly. Yep. Alright. So now we go back to program data and modify this position, and that will be okay. So now our actual home position will be set, or rather the work object will be set. We'll repeat the same thing for the B, and we'll actually have both of these work objects set. So moving on, we actually have to define the points in which we want to go. So we could actually manually enter these in, but because we know the size of these pallets and where the center points are, we can enter it in just using some simple tricks. So we'll go back to the jogging menu, ensure that we have tool 1 set here. We're going to change our work object to work object A, and then we're going to go back to program data, view program data types, go to robot target, double click it, and A1. Now, this X and Y and Z is relative to the current work object that we're set in. So all we have to do is enter in 20, 20, and 0. And hit OK. So after we've configured our position A and B using our controller, we're now going to set the intermediate position as well as the safe position just using the jog command. So first things first, we're going to want to make sure that our controller is actually enabled, so we're going to go to manual off of operating mode and hit enable device. So now if we go to the jog, we can actually move the robot as we want. So hit acknowledge. So now we can move the robot back and forth. I'm going to move it to a little bit of a faster position there. And we can see the robot moving. Now, given that our work areas are here and we're sufficiently high up, we can actually set this as our safe position. And the way we do that is by going to Program Data. We're going to go down to Robe Target. We're going to hit New. We're going to name it Safe Position. We're going to change it to a global. Storage type should be a persistent, because we want this to persist after the program. Task is this, yes, 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 so hit OK. So now, in order to save the intermediary position, what we're actually going to do is we're going to bring the robot down using the jog function. That's bringing it up. So we're going to bring the robot down so that it's closer to, but not hitting those. So right about there seems fine. So once again, we'll do the same process of going to Program Data, hitting New. We're going to name this one Intermediate. We're going to once again use all these, hit OK, and it will also record this value. And that's how we recorded our rope targets.
So this is our rapid code. As you can see, we have 2 work objects, one for each of the pallets, 2 rope targets, one for each of the starting positions at the pallets, an intermediate point, a safe position, and our tool data for the end-effector. For our procedure, our pick and place function, we have 4 parameters: our pickup location with its corresponding starting work object, and our place position with its ending work object. So first, for our procedure, we wanted to make sure that the gripper was open. Otherwise, when we get to our pickup position and it tried to pick up and it was closed, then we wouldn't actually be picking up an object. So first we reset the gripper and make sure it was open, and then we proceeded to actually move to that pickup position. So our first move L offset is to move to a safe position right above the point where we want to pick up the object. So that's what the offset function is for. We give it 4 parameters: our actual rope target, which is our pickup location, and then our offset positions, which are X, Y, and Z. In our case, we have 20 millimeters right above our object to avoid the gripper from crashing into it on its way to the object. From there, we actually move down to pick up the object, and we close the gripper, give it a little time to actually actuate, and then we move back up to that offset position. You can see in the comments next to the code what each of them do as a supplementary thing. So from there, we move to our intermediate point, which is somewhat optional, but we wanted, in the case of our work objects being in different positions, we wanted to make sure that there's an intermediate point so it wouldn't actually crash into anything in between the work objects. So we move to our intermediate point, and then we do the same procedure for our place. So it's basically the same thing where you move to an offset position right above our place position, move it down, open the gripper, and then move it back above to that safe position so it wouldn't crash into the object, and then we move back to our intermediate point. So moving on to our main function, we first find our width, and our width is a constant number. It's our distance between the centers of our points on the pallet. And from there, we move to our main position, or our safe position, and that's to prevent the gripper from crashing into anything before we run our code. From our safe position, we actually run our pick and place to go from A1 to B1, from B1 to A2, from A2 to B2, so on until B9. You can do it two different ways. You can have two nested for loops where you have your Y position and your X position going from 1 to 3 or 0 to 2, depending on how your offsets work. But I did it from 0 to 8, which is essentially 1 to 9. But we started at 0 to make sure our offset begins at our first point. So from there, we actually run our pick and place to go from A1 to B1. And that's where we once again to use offsets. Since we are going from 0 to 8, we want to make sure that the offset loops from 0 to 2 in the X and Y, and we can do that using modulus and using division. So how modulus works is given two numbers, say 5 and 3, 5 mod 3 gives the remainder. And I have a graph over here to show how that works. So for X mod 3, given our X value from 0 to 8, our modulus will go from 0, 1 to 2, 0, 1 to 2, 0, 1 to 2. And that defines all our X positions. For our division, we can use that to define our Y positions. So once again, from our X values from 0 to 8, our division will actually give us something different. So for example, 1 divided by 3 is 0.333 repeating, but I can use the truncate function, so I get only an integer, and from there I can actually get our Y positions. So looking at this table, we can actually see what our coordinates will be, and they will correspond to our actual pallet from this chart. So we use our offsets. We offset it by that calculation, whether it be modulus or our division function, and we will multiply it by our actual width to offset our x's and y's from our original position based on what position we're on. So if it's on B2, we'll offset our x by 1, but our y by 0. And one thing to note is for each of our starting positions, we want to make sure we are in the right work object, otherwise you will run into an error. Moving on, for our for loop, we want to go from our B position back to our A palette. So we have our edge case, which is when we are at our second or third row, depending on how you look at it, for our X positions. From there, we want to move back to our initial row, but a next Y column. So our edge case makes sure that we actually do that. We start from the same B position we were on, and we will reset our X, and we'll increment our Y. Otherwise, for all our other cases, we will just continue on and increment our X without incrementing our Y. And then finally at the end, when we are at position B9, we move back to our initial position A1. So if the program is looping, it'll continue to pick and place from the beginning. And when the for loop ends, we'll go back to our safe position and prepare for any next robot commands.